Hey everyone, welcome to the recorded class of our gear chapter. This is in Shigli. If you follow Shigli, this is chapter 6 and 7. I will be mixing the contents of a lot of books. So let's start. So this is our topic on gears. Okay, I will break down this whole topic into two parts. One will basically be discussing everything about the basics of gears, basics. And in other topic, we will be actually doing calculations based on like multiple years. Okay, calculations based on multiple years. Okay, so let's start. Introduction to gears. Uh, by this time, you should have already completed your like mom lab experiment on gears, and I have already shown you many of the like gears, and you have seen them in real life. You understand some of their properties, so this should be kind of like a revision for you. So basically, as you already know, gears are machines or elements or links or any form of like part of a machinery, so that's used to transmit rotational motion between two shafts. Now, between two rotating, like shafts that may be parallel at an angle or in any other, like orientation, depending on your desired outcome. And usually, so the input and the out always rotate at a constant speed ratio. So in this course, in our mechanics of machine course, we will be mainly always be using only four types of gears: spark gears, helical gears, bevel, and worm gear. Okay, so there are many more different types of gears, and detailed calculation, mathematics on everything based on these gears will be done in your design machine design two course, not one. Okay, machine design two course. But we will be mainly looking into some like functions of this function of these gears. Okay, a minute, my exam. So you are going to be studying all of this in your machine design two course, more detail, more calculations and everything. Okay. Let's look at the first one, the helical gear. Okay. So sorry, the spark gears. Okay. So these are, as we have already seen, these are spark gears where the teeth are straight, and two spark gears basically, in order to transmit power, rotation, motion, two spark gears must mate. Okay. So this is mate or meshing, whatever you call it, mating gears or meshing of gears, whatever you call it. Okay. As you can observe, the shafts, the rotating shaft, the power transmitting shaft of the two mating gears are okay. So now this is an example of helical gear, same as a spark gear. The shafts of the helical gears are parallel to one another. However, unlike spark gears whose teeth are actually straight cuts on the cylindrical surface, helical gears teeth are cut at an angle. Basically, each teeth is part of a bigger helix. Okay, each teeth is at an angle. And these are two examples of bevel gears. So bevel gears are basically, special kind of gears where the shafts are, are rotating about, where the gears are basically rotating about shafts that intersect. Okay. The shafts of the two gears. This is the shaft of one gear. This is the shaft of the other gear. These shafts, they are not parallel. They intersect. They intersect. And one thing I want to tell you is that the shafts intersecting may be perpendicular or maybe at any other angle. Okay, maybe at any other angle. It's not mandatory that they must all any other angle. It's not mandatory that they always have to be 90 degree. Okay, so these are bevel gears. Now, bevel gears can also have straight teeth. These are called straight bevel gears. And bevel gears can also be of helical type. These teeth, instead of being straight, can be at an angle. And those are helical bevel gears. And the last one is the worm gear. You have already seen the worm gear where the worm, the top, like input or the pinion worm usually have one, like teeth altogether. And this is sometimes called the worm gear or worm wheel. Okay, so it's actually like referred to by both those names. And the special characteristics of worm gears are it's actually because of the huge difference in teeth number between the worm and the worm gear, they actually give you a very high velocity ratio. So these are some, like easy descriptions and some properties of spark gears. You can go through this. I will just, discuss some basic points. So spark gears are the most common type of gears. They transmit power between parallel shafts, and they are very cheap, easy to manufacture. How, as you already know, because the teeth are straight, less contact area, so they produce very huge noises, and they're used in everything. Okay, like everything. And helical gears, okay. So helical gears have angle teeth, and as you know, because of the angle teeth, there are, like more contact area. So gradual tooth contact occurs. That's why less vibration, less noise, more strength, and all that. However, another thing happens because in helical gear, the teeth are at an angle. So what happens is, if I explain that to you, let's say, and let me go back to helical surface. Okay, because the teeth are at an angle, what happens is these forces, whenever two gears mesh, there is a force acting on the opposite gear, an action force, and this force is at an angle. So it has a radial component and an axial component. And this axial component kind of like, puts an axial thrust force on the shaft. So if this is your gear, so let's say if this is your shaft and your gear is rotating in that shaft, because of the teeth, the force generated on the gear is at an angle, and that leads to a radial force and an axial force. This axial thrust force is actually problematic because it's put some kind of force on the whole shaft. Basically, it makes the shaft lose contact at its fixed. That's why there is a huge friction development that can actually like break over the whole shaft from the motor. So you need to use bearings in order to very strong bearings in order to reduce the effect of this axial thrust force. Okay. So this is one disadvantage of helical gears. Okay, it produces axial thrust force, requiring additional bearing thrust forces. And one very popular way to actually reduce this, axial thrust force are to use herringbone gear. Okay, herringbone gears. You know that herringbone gears are basically two helical gears of opposite angles. If one of the teeth is like this, the other, like helical gear will have teeth in the opposite direction, right? And herringbones basically in gears, these two helical gears are merged together. So what happens is this helical angle produce, let's say, force in this direction, and this helix angle produce force in the opposite direction. And those axial forces are cancelled out. Okay, so in Herringbone gears, the disadvantage of helical gear don't exist anymore. And helical gears are used in everywhere because of their like strong like lifespan, uh, less vibration, less noise. They are mainly used in automotive transmission, ships, conveyor belts, industry machineries, and everything. Firstly, bevel gear. So bevel gear is very popularly used in automobile differentials, in large scale industries, power plants, ships, and everywhere. And bevel gears can be of many types. They can be straight bevel gears, they can be spiral, helical, and all that. And they can actually transmit by 90 degree, but it's not specifically 90 degree. The condition is they transmit power between intersecting shafts. Okay, intersecting shafts, that's the main. Okay, so they're very efficient, they can carry a huge load and all. So and lastly, worm gear. As you already know, worm gears actually they give you high velocity reduction. They transmit power between non-intersecting shafts, and they're used in elevators, conveyors, like packaging industries. Yeah, packaging industries and many places. If you have understood up until this point, so let's look into uh, more complex. Okay, so when you look at a gear, you may think of a gear is kind of like a circular object with some teeth cut into it. Okay, very simple. But that's not the case. Each teeth and all the dimensions, the way the teeth are cut into the gear and the distance between one another, and even this circular like base of the gear, every one of them has been intricately designed, has specific dimensional properties that define a gear and actually ultimately leads to its function. Okay. So it's very important when you deal with gears, you actually understand what are the specific names of each part of a gear. Okay, each part of a gear. So let's look into the names of each part of a gear. Okay, so this is let's say if I show you a gear, any gear, let's say this is a gear, and let's say I just picked out this portion and I'm zooming it out and showing it to you over here. Okay, so that will actually help us know all of the terminologies for a gear. So let's see. So if like how gears are basically teeth cut onto a cylinder, teeth cut into a cylinder. So this top flat surface is called a top plane. Okay. And similarly, the bottom surface of the gear is called the bottom line. Okay. And whenever you deal with gears, you have to know of some very special circles. So circles are very important when you're, like actually talking about gears, circles. And there are actually five circles that you have to know when you're actually dealing with gears. So the circle that you can make from the top edge, the circle that goes to the top edge of the gear, the circle is called the addendum circle. This addendum circle, the circle that goes to the top edge of the gear, is called the addendum circle. The circle that goes to the bottom edge of the gear, like gear teeth, the circle, I'm showing it in both of the slides. Okay, so on the bottom slide and the top slide, I think both of them should be visible to you. So the circle that goes to the bottom of the teeth is called the dedendum circle. Okay, this is the dedendum circle. Okay, and so there's another circle, a very special circle that does not actually exist on the gear. It's actually a hypothetical, not a hypothetical, it's an imaginary circle. Okay, it's an imaginary circle. So that doesn't exist specifically on the gear, but it's very important. Okay, so basically, this is that circle. I'm showing it to you. This is that circle. So this circle is called a pitch circle. Now, pitch circle is special because basically whenever I'm like showing you to another, let's say, whenever two gears meet, I'm showing you two gears over here. What happens is, whenever two gears meet, if you look over here, two gears are meshing, right? So you can see how their teeth are meshing over here, right? But what happens is, do you see that I can actually make a circle over here? That a circle that goes through the middle of all the teeth, and similarly there's another circle that kind of goes through the middle of all the other teeth in the mating gear. And what happens is, whenever gears mesh, they transmit motion and power. Those imaginary circles are always in contact, kind of like rolling circles. Okay, whenever I say, we talked about rolling contact. So this point is always in contact during rolling contact when we did velocity analysis, all that. So whenever gears mesh, these imaginary circles are the one that remains in contact. Okay, are rolling. That's why these circles are so important. These circles are always in contact. They are tangent to one another, and also for the fact that all the calculations you are going to do will be done on these circles. All the calculation we will do. So calculations for gears are mostly done in this pitch circle. So addendum circle, dedendum circle, pitch circle. Okay. Now there is another circle that is actually a little above the dedendum circle. If this is the bottom circle, the dedendum circle, just a little above that, there is another circle called the clearance circle. Now, this clearance circle, this circle is called the clearance. So the purpose of the clearance circle is basically to ensure that, whenever this is one gear, right? And in order to pair it up, I will be having another gear meshing with it. Now, if that gear's top surface, if that gear's addendum, if that gear's addendum kind of, like touches my bottom land, there will be huge friction. So I don't want addendum of my gear one to mesh with my dedendum or to touch my dedendum of gear two. Otherwise, there will be huge friction and huge wear and tear, and your gear won't even last for, let's say, 5 days. That's why you always ensure whenever gear mesh, they only, touch at one point. Okay. Contact power transmission is done at a point, not on a surface level. So what happens is we make sure that these two things, they don't touch another. That's why that there is some gap kept when meshing happens. So the addendum meshes with the clearance circle. It's a hypothetical circle, clearance circle. It's not in the gear, but it's a space given there. Okay. So then we have gone to, addendum, dedendum. Okay, so let's go for the other things. Okay, so the gear, this pitch circle, the side of the gear above the pitch circle is called face, and the side of the gear below the pitch circle is called the flank. And okay, so move on to now let's move on to some more, better definitions that we need for calculations. Over here, two teeth are shown, right? I have two teeth. This is teeth one and teeth two. Okay. So on the pitch circle, I told you all calculations are made on pitch circle. So on the pitch circle, if you select one point and you move on to on one particular teeth, you select this point one, and you select a similar point on the second on the second teeth. Okay, a similar. The distance between these two, this distance is called a circular pitch. Okay, it's called a circular pitch, and this circular pitch is denoted by small letter p. Okay, and it's a very important, term, and that's used in calculations for gear design. So, and what will be the value of circular pitch? So from here, from the definition, from one point of a teeth to another teeth, I can say that circular pitch, circular teeth can be written as this one. So basically from one point of one teeth to the next. So what will be circular pitch? The total perimeter. What is perimeter? 2 pi r, or what? Pi d divided by the total number of teeth. Now I told you, you remember, number of teeth can be denoted using t or using n. This is more popular, okay? And when you refer to RPM, we usually use the small n. Okay, so n is actually more in many books you will find n refers to the teeth number. That's why I gave it in your lab exams and everything. Okay, so number of teeth, where n is the number of teeth. That will give you your circular pitch. Okay, this is the circular pitch. Now, similar to this one, let's say if you select one point on teeth and like the extreme point on the teeth, if you want to measure this distance, that is the tooth thickness. Usually tooth thickness is t, small t, and it's usually circular pitch by 2. Okay, now between each two side by side teeth, there is a space given here. The length of this space is called the length of this, or the width of this space, is called the width of space. The width of space is actually kept for the meshing. And whenever two gears mesh, the width of space of one gear must match the tooth size. Of course, the other gear's tooth must fit here. So must match the tooth size of the meshing gear. Okay. So width of space must match the tooth size of the meshing gear. Now let's look into some other definitions. Okay, again erasing this one. So, so let's see. Now, from the circular circle, this is a circular pitch circle, right? And this is the addendum circle. The distance between them is referred to as addendum, denoted by A. This is the pitch circle. This is the dedendum circle. The distance between them is referred to as B. The dedendum, okay, is referred to as dedendum, denoted by B. Why B? Because usually the letter D refers to diameter. That's why you cannot use D. We use B. Now, the distance between this distance, the clearance distance is called denoted by C, clearance. Okay, and I will give you the formulas for each one of them. We are coming into in a bit. So whenever you're dealing with gears, there's another very important definition that you must get. And this particular, parameter cannot be found on the gear itself. Okay, it's not on the gear. You cannot calculate on the gear, but it comes from other, like concepts and derivation. What is it? It's called the diametral pitch. Okay, diametral pitch. Now, diametral pitch is denoted by a capital P. Okay, so do not mix circular pitch, small p, with diametral pitch, capital P. Okay, and they're also related to one another. I will come on to it later. Okay, so what is diametral pitch? Okay, diametral pitch actually refers to tooth size. Tooth size. How big are your tooths? Your gears can have big tooth and small tooth. So tooth size is actually denoted by your diametral pitch, and diametral pitch refers to tooth size in FPS unit. Okay, US customary unit. And if you want to denote diametral pitch in SI unit, that is denoted by something called module. Module, comma M. Okay. In module M denotes tooth size in SI unit, and diametral pitch capital P denotes tooth size in FPS unit. Okay. Inch and foot and something like that. Okay. And M is usually the inverse of diametral pitch. This is another relation you need to know. Okay. So why is diametral pitch so important? So what happens is whenever two gears mesh, okay, so over here two gears are meshing successfully, they can transmit motion from one to another. These two gears, you should know, if they have successfully meshed, they have the same diametral pitch, same, okay. If two gears do not have, P1 is not equals to P2, then they cannot mesh, okay. You cannot successfully mesh. So remember, whenever you're designing a gear and those two gears must mesh together to bring about, motion transfer, their diametral pitch must be same. Okay. So that's a very important fact, So let us try to derive the formula for diametral pitch. So I told you diametral pitch is tooth size. So what can be tooth size? Tooth size is simply what? So diametral pitch is equals to referred to as the number of teeth divided by the diameter. Okay. And by the way, whenever I just write diameter, it's always the pitch circle diameter. Okay, this is always the pitch circle diameter. Okay, diameter. Okay. So diametral pitch is equals to n by d, the pitch circle diameter. And what happens if you notice, if the diametral pitch value increases, then that means what? To to make this relation true, the number of tooth must increase for the same diameter circle. So that's why we say that as diametral pitch increases, the number of tooth increase, and that's why tooth size decrease. So there is a figure that shows this over here. See, this is the relationship between diameter. You can see when the diametral pitch is 6, look at the tooth size. And look at the stark difference when the diametral pitch value, P value, is equals to 36. Do you see how small the tooths are? Now there are more teeth, but each tooth has a very small size. Okay. And from this two definition, if you know diametral pitch is equals to n by d, and circular pitch is equals to pi. Okay, let me use a small d. I just use a small d. Pi d by n. So can I say circular pitch is equals to nothing but pi by diametral pitch? This relation is also important. Okay, so you need to know all these relationships. Now, addendum. Recall addendum. This distance. Addendum is equals to 1 by diametral pitch is equals to modulo. Okay, dedendum is equals to 1.25 by diametral pitch. Diametral pitch. So I'm writing this again. A is equals to 1 by diametral pitch. B is equals to 1.25 by diametral pitch. And there's something called hole depth. So we call this, like hole depth. Hole depth. Okay. Hole depth is nothing but A plus B. Sorry, A plus B. And clearance is the amount that is left, like to difference between, mating pair addendums and dedendum. Clearance is basically B minus is equals to what? If you use this formula, clearance come up to be 0.25 divided by diametral pitch. Okay, so that should cover up the basic definitions of gears. Now, let's talk about what happens when gears are meshing. So this is a very important factor to talk about when gears are meshing. So let's look into this figure. These two figures, this one and this one are basically the same figure, just like drawn from taken from different books and for different instances, just for better understanding and better like concept. Okay. So what happens is over here we have, and I told you like one always refers to the fixed link, right? So we never use one to refer to the gears. So you can use gear two and gear three and gear four and so on, where two is the input and the other gear is out, okay, or the driven. So over here, they have selected gear two, whose center is over here, and this is the driving gear. Driving gear are also called pinion, okay? And there's another gear who is actually getting the motion from the initial pinion. That is called a driven gear, and driven gears are simply called gears. Okay. So whenever I talk about or we talk about any gears, you need to. I told you there are many circles, right? That you need to talk about. So we already talked about 3 to 4 circles, I think. So there's another circle that you need to know about. That is called the base circle. Okay, base circle. Okay. So the specialty of base circle is that if this is your teeth. Now, your teeth, gear teeth can have, different shapes. Now, there's a very special shape called involute profile. Okay, involute profile. And this shape doesn't start from the base of the teeth. This involute profile shape starts somewhere from the teeth. Okay, so if this is your teeth, this is where the involute profile starts. Okay, so the starting of the involute profile starts from here, and this whole shape of the teeth is actually involute. The circle that goes to the starting of this involute profile is called the base circle. Base circle. So the circle, base circle is nothing but circle from which involute profile starts. Okay, that's the basically. So if I said this is the base of the gear, this is tooth, and involute start from here. This is the base circle. Okay, so if you're clear up until here, so let's see. Okay, so another thing you need to know is let's look at other circles over here. Okay, if you know the base circle, let's try to see where the circles are. I'll try to color code them so that it's easier for you to understand. Okay, so basically, this is the let's use red to refer to our pitch circles. So I told you whenever these two gears are meshing, right? And whenever two gears mesh, their pitch circles are tangent to one another, are in contact. So this is denoted by this, line, okay? This hashed line. This is the pitch circle of the driven gear, okay? Gear three. I am just following this line and color coding them for you so it's easier for you to understand. Okay. And similarly, of course, the bottom gear, the driver gear also has a pitch circle. This is this one. And you can see how the pitch circles of the two gears are in contact, right? They're always in contact, they're tangent, and this is the imaginary circle, okay? Now, let's use green to refer to the base circle. So base circle is basically this one, okay? This solid line. From this point, the involute profile starts, okay? And from this point, the involute profile of the other mating gear starts. So this is the base circle of gear 2. This is the base circle of gear 2. Similarly, this is the base circle of gear 3. Okay? This is the base circle of gear 3. I hope this clears up, some of your, concepts about each of the circles and everything. So let's look for another color, let's say pink. Okay, so now let's look at the addendum circle. Okay. So as you see, let's look at addendum of gear 3. Where is addendum of gear 3? It's of course above the pitch circle. This is the addendum of gear 3. Okay. This is the addendum circle. This is the addendum circle. It's marked here. This is the addendum circle of gear 3. This is the addendum circle. So, and let's look for the dedendum of gear, like 2. So this is the base of dedendum of gear 2. And this is the base of, or not base, sorry, dedendum of gear 3. And do you see how the addendum and dedendum of opposite gears? This is the addendum of gear 3. This is the dedendum of gear 2. Do you see how there is some space between them? And I told you this is the clearance, because if they mesh, there is going to be huge friction. You don't want them to touch one another. Okay. And this is obvious. So this is the what? This is the addendum of gear 2. Okay. So these are the things that you need to know. Now, so if you have actually marked this out, so let's look for other things. So let's look at some other definitions. Okay, what happens when gears are in contact? What are the possible problems that can occur? What is line of action? Let's look into some other definitions. So I'm going to use another color because I've already used most of the colors over here. So let's go for a blue color. Okay, so from one center to the other center of the two gears, this is called a center line. And the tangent to the pitch circle, this circle is called the tangent. It's simply the tangent. Okay. If you draw tangent to the pitch circle, this is nothing but the tangent. And the gears usually have an involute profile. Now, the involute profile makes the gear so special that the contact point, let's say, each time, whenever, like if I show you, this figure, again, if I show you this figure, the gears are in contact. Currently, this point is a contact point, right? And now this one is slightly in contact. As the gears are rotating, this contact point kind of shifts, right? And if you trace the contact point, if you stop the contact point and follow it, you are going to be observing a very interesting phenomenon. Okay, you will see that the contact point makes a straight. And another interesting fact is that straight line is actually tangent to the base circle. Okay, a tangent to the base circle. Clear? So let's show it in another figure. So first I will show you that if you actually trace it, what happens. So there's a video for you here. So let's actually see the video. Okay, this is the PDF one. So you can actually simply go to the link over here. Mm, make a bigger state of the leaves. Mm, okay, so wait a minute. I will open the video. Okay. Okay, so let's see over here. So let's say you follow this point, okay? So this is, let's say this is the contact point. You try to follow this one and you can see this point, the next contact point, This is a starting, as the contact point of gear starts and it kind of like remains in contact and it lets go, that contact point always remains on the same line. See, this is the start of contact. The contact is still ongoing and this contact is letting go, right? And the next contact is happening and the next one and so on and on. If you trace this path, just follow this. Contact happens, remains, let's go. The next contact happens, remains, let's go. Everything happens in the same line. Okay, everything is happening in this straight line. Okay, so this line is called the line of action. Okay, this is the line of action. This is the line where, like the action and the reaction forces are basically, taking place. The main motion transfer, force transfer happens through this line. And I told you that the specialty is this line is basically a tangent to the base circle. Okay, so we have already gone through this one. So let's look at this one. This is the same figure where again there is a Dedekind circle, there is a pitch circle, there is a base circle, there is an Adam circle, and everything. So I will only, make recolor the base circle and the pitch circle. Okay. So where is the pitch circle? Let's look at the pitch circle. So this is the pitch circle. Okay, over here, this one is a pitch circle. Okay. So let's increase the thickness a little bit. It's easier to follow this. And similarly over here, this is the pitch circle, okay? And you can see how the pitch circles are remaining in contact, okay? And let's like draw the base circle. So over here, this is the base circle. Over here, this green guy is the base circle. And this one is the base circle, okay? I'm not going to I'm not tracing the whole thing, just the ones that are interesting, okay? Important to you. Okay, so now you will see the interesting fact that line of action is a point that where the teeth always have to like remain in contact, right? So if you draw the line of action, this is the line of action, and in reality this line of action, can you see that at this point and at this point it's tangent to the base circle. So basically at this point the line of action is line of action is a line that is tangent to the base circle and intersects the center line. This is the center line at a point on the pitch circle called P. This is called the pitch point P. Okay. It intersect the line of centers pitch at the pitch. Okay. Now, if I draw a tangent to the pitch circle. This line is a tangent to the pitch circle, and this is the line of action. The angle between these two lines, the line of action and the tangent to the pitch circle. So the angle between line of action and tangent to the to the pitch circle is called the pressure angle. And this pressure angle is another very important, like dimension to design gears. This angle denoted by phi is called pressure angle. Okay. So whenever we are going to deal with gears and everything, this is an angle that is like very important to you. Okay. So and this angle also helps us in another way. If you use simple geometry, you would notice that if this line is a tangent to the base circle, then if I connect it to the center, this is what? This is basically the radius of the base circle. This point is what? The radius of the pitch circle, and we don't usually use any subscript to denote the pitch circle. If you write D and there is no subscript, it's automatically pitch circle diameter. Okay, pitch circle diameter. If I use DB, it means base circle diameter. Okay, base circle diameter. If you use DA, addendum circle diameter, and so on. Okay. So now let's see. If this is the RB and this is R, of course, if this angle is phi, that means this angle is phi. That means using geometry, this angle is phi. So we say the relationship between base circle and pitch circle is that the base circle radius is equals to the pitch circle radius cos phi. Okay, this is another important formula that you will be knowing. It will be requiring later to design gears. Okay, and of course, the base circle diameter and the pitch circle diameters for the input and the output gears may vary. So we say RBP is equals to RPP cos phi for the pinion, basically omega for the gear 2, and we use RBG is equals to RPG cos phi for the driver gear, okay, for the output omega 3. Okay, so if you have learned up until this far, so like let's go for another ruling called the fundamental law of gearing. Another thing is before I start this one, uh, just now, we saw how the base circle radius and pitch circle radius have a relationship. The same relationship also applies to circular pitch. Circular pitch. Now you know circular pitch is denoted by what? Small p. So if I want to find out the circular pitch of the base circle, like where the base circle, like imagine a circular pitch, then it will be same. The pitch circle circular pitch, basically the original circular pitch into cos phi. The same definition, like a relax. Okay. So let's go for this one, fundamental law of gearing. Okay. So what happens, what is fundamental law of gearing is that basically when two shapes or any, bodies, basically they're in contact, for them to remain, when two bodies, mesh or, contacts. So, in order to, reduce, in order for them to remain in contact and, remove any vibration problems, a certain condition has to be made. Okay. Basically, whenever, let's say this is input, so this is the input rotating at body omega 2, angular velocity omega 2, and this is the another body rotating at omega 3. So for them to remain in contact and reduce vibration noise problems, you must always ensure that whatever omega 3 is, doesn't matter. But the ratio between the two must always be same. Okay. If this happens, if you can ensure that the ratio between the input by output is always constant, then they will always remain in contact and like the vibration problems will basically be reduced. Okay. So this is basically the main fundamental law of gear, that whenever any gears mesh, we want to reduce vibration problems. So we must ensure that these ratios are remaining same. Okay? And for you to do that, you must design the surface of the two, like input and output in such a way, because not all shapes will give you this one, because you design any random arbitrary shape, and you design any arbitrary shape rho, they are not going to give you omega 2 by input by output is equals to same for every single, values. Okay, so always, it's not going to happen. So in order to do that, you must design the surface in a special way. And that special surface are called conjugate surface. Okay. So let's say when a tooth profiles of mating gear are shaped to produce a constant angular velocity ratio between the two shafts, then the two mating surfaces are said to be conjugate. We call them conjugate surface. Now, whenever I talk about gears, gears are of course conjugate surface. Conjugate surface. Okay. That means the ratio of velocity between input by output will always be same, no matter what the values are. Okay. So now there is law that states that what is conjugate surface? How is conjugate surface ensuring that this velocity ratio remains the same? Okay. The thing is, remember, if I, just go a few slides, back, notice that I showed you that, whenever two gears mesh, there's a line of action and there's a pitch circle, like tangent and the center of line of centers, right? And I told you that the line of action meets the line of center at a point called P, the pitch point. So the conjugate surface states that, let me first go through it, then, like I will explain it. The law of conjugate action states that if the common normal at all points of contact of two gears intersects the line of centers at the same point, then the conjugate action is achieved and the output shell will rotate at a constant speed for a constant input shell. Basically, it states that if this is your tangent of contact, and then this will be the normal of the contact, this normal must always intersect. This is the central center of the input gear, and this is the center of the output gear. This line of action must always intersect the line of, this is actually this common normal is kind of like the line of action for arbitrary shapes. This line of action must always intersect this line of centers at this particular point, which is a pitch point. It cannot be, the pitch point cannot move. The pitch point must remain stationary at the same point. If you can achieve that, then the shape you just produced are conjugate. Okay. Now, what happens is, in reality, you can produce a lot of shapes and you can ensure that your pitch point remains fixed at this stationary point. However, these, you can, if you just imagine these surfaces to be moving, you can see at the next instant, this contact point comes over here, right? And then this becomes a tangent and this becomes a normal. So the line of action for conjugate surfaces can move as long as they cut the line of centers at the pitch point. Line of actions line of actions can move, okay, can change locations, but still ensure that the input by output velocity ratio is same. Can follow the law of gearing, but the line of action can still move. However, involute profile involute profile are a special conjugate surface where the line of action doesn't move. Okay, it remains fixed in a straight line that we just saw. It remains fixed in the same line. In other gears, if because your the gear teeth we try to design, they have involute profile, the line of action doesn't move and the pitch point remains the pitch point, but the line of action doesn't move. However, if they went into gear shape, involute shape, this line of action can be over here. At another point, it can be over here, here, here. It could have moved. Okay? So that's what it means to have conjugate surface. All involute profiles are conjugate surface, but not all conjugate surfaces are involute profiles. Basically, by having involute profiles in our gear, we ensure two things. One of them is that the ratio between the input to output velocity is constant, and another thing that the line of action is remains, like in a single line, it doesn't move. Okay. So if you do not follow these parameters, if the law of gearing is not followed, serious vibration and impact problems would result, even when your velocity of, like transmission is very good. So this is just summary again. I will just go through it with you. The fundamental law of gearing says that as gears go through their mesh, the pitch point must remain stationary on the line of action so that the ratio of speed between the input to the output remains constant. This means that the line of action for every new instantaneous point of contact must always pass through the stationary point P. If this does not happen, if you do not wish to follow the fundamental law of gearing, then yeah, these problems will happen. So we always try to make sure that yes, our gears should fundamentally be, should have conjugate surface, preferably involute profile to ensure this phenomenon is prevented. So, what is involute profile? How to draw it? Okay, usually in lab, we used to have another experiment called experiment of loci, but this is a very easy experiment, so we skipped it this time, and inshallah we won't be doing it anymore. So Involute profile is a special profile. To define it is basically if you have a circle and you kind of wind, wrap a string around the circumference of the circle, okay? And then you use a pin to hold one point of the string. This is a string, okay? This is a string on the circle, and you start unwrapping or you start unwinding this string while you hold the pen over here. Then the path, and you are unwinding, okay? At this point, the string is like this. In the next second, the string is like this. In the next second, the string is like this. As you unwinding the string, the trace that the pen is making is the involute. Okay, this is the trace it's gonna make. This is the this path is the involute. Okay. Of course, your gear doesn't have this whole profile. It only uses up the initial part of the involute profile. But this shape is known as involute profile, kind of like a spiral Uzumaki shape kind of thing. Okay. So, geometrical construction of spiral in Japanese is like referred to as sometimes Uzumaki. Okay. So, okay. So how to do this is the involute. Okay, this is how it's supposed to look like. So you can also draw it using geometry. Basically, you divide your whole circle into certain equal divisions. From each point, you draw a tangent, and starting from this point to the next one, you measure this distance, and d- from here, cut this distance. Okay, again, measure from here to here. From this point, cut on the tangent, and so on and on until then you join all these intersecting points and you get your desired involute profile. So, okay. So we have some more definitions to go. One of them is about contact length, and another one is our contact ratio. Okay, contact ratio. Okay. So, what is contact length and what is contact ratio? Okay. So, what happens is, okay, whenever your two gears are meshing, okay, I will go, this slide, I will go back to this slide where the gears are meshing. Whenever we have, like two gears and they are meshing together, what happens is, if you notice, this was the addendum circle of the output gear, and this was the addendum circle of the input gear. You will notice that the addendum circles, opposite addendum circles match at one point. So the addendum circle of gear 3 somehow at one point coincides with the base circle. Let's look at the base circle. This solid line was our base circle, right? And again, this solid line was our base circle. You'll notice that the addendum circles of opposite gears, the addendum circle of the gear 3 matches with the base circle of gear 1 at a certain point. Let's call it C. Again, the addendum circle of gear 2 matches with the base circle of gear 3 at another point, okay, which is the point B. This distance, this distance between the this distance is called a contact length. Okay, contact length denoted by usually it's denoted by I think LAB. Yes, it's denoted by LAB or whatever you call it. It's basically L. Okay, the contact length. Why is it called the contact length? Because only when the opposite addendum and base circle mesh at this point comes into contact is when your teeth contact starts. Your teeth contact starts. And this contact, we saw video, right? We saw video where like over here, the teeth have started contacting. So we saw video where the teeth, start contacting. This is the point C, and it remains in contact, remains in contact, remains in contact, and it lets go point D. Start of engagement of teeth, start of engagement point C remains for the whole contact length. Start of disengagement D. So over here, the same thing happens. So at this point, our teeth just came into contact, remained in contact toward the left, and at this point, disengagement of teeth. So this whole length is actually the contact length. And if you have understood this one, so basically we usually use other definitions to refer, to actually derive this, length and all everything. So let's go through those ones. So let's go for another definition called contact ratio. Okay. So gear tooth starts contact at point C, what we have known, and ends at point D, what we have just done. Point contact point starts over here. This whole length is the contact length. It ends at point D. And you'll notice that this length kind of passed through the pitch point. You remember pitch point? Pitch point P, where the line of action meets the line of centers, pitch point. The number of teeth that remains contact along the pressure line at a given point of time is defined by the contact ratio. Now, contact ratio is also called denoted by MC. Now, I told you from C to D is that length for which the gears remain, the one length for which the teeth remain in contact. However, if you notice, look, at this point, at this instant, this teeth is in contact and this teeth is has just started contact. At this point, isn't there two teeth in contact simultaneously? This is called contact ratio. Contact ratio states at any point, how many teeth are in contact. Okay. Now there are formulas to find it out, and we usually say that whenever basically if I go back to this one, you will say we actually call this we have some arcs that if and whenever the teeth starts contacting for a certain limit, we call it arc of approach, and as it's leaving disengagement, we call it arc of recess. And from here, if you actually use geometry, this is the point P, this is the point C, this is called CP, this length is CP, this length is PD. Okay, so CP and PD, and there is some arcs. If you use geometry and the pressure angle and everything, you can look in Shigley. In Shigley, it's actually very properly explained and derived. I won't go for the derivation. Again, there's another figure that shows what is the arc of approach and what is the arc of recess. Basically this length is called CP, is the arc of approach, and this length PD is the arc of recess. Use pressure angle, geometry and everything to derive this. Okay, where the contact ratio, like the number of teeth that's in contact at any given point, MC is denoted by the contact length. What is the contact length? This whole length is the contact length. So L, or you can call it CD, length CD, divided by base circle pitch. This is small p, okay? This is base pitch. We call this one base pitch. Normal p is circular pitch. This is base pitch. And you know what is base pitch? We just went through base pitch. Base pitch is equals to circular pitch cos phi. And what is contact length? CD can be divided into 2 parts. CD is nothing but CP plus PD, where CP is the arc of approach and PD is the arc of recess. So CP can be derived using this formula and PD can be derived using this. And what is R3 and R2? 2 is the input gear and 3 is the output gear. So R3 refers to the, I told you, there is no, like subscript, right? So radius, basically pitch radius, okay? Pitch circle radius of the output gear. R2 is pitch circle radius of the input. Phi is the pressure angle, A is the addendum. Addendum of, if like I told you, whenever two gears move, their diametral pitch must be same. And A was what? 1 by P. If their diametral pitches are same, of course there are two gears for them to mesh. Their addendum must also be same. So A is the addendum. R, phi, sine and all the geometry. Using these two formulas, you have to know these two formulas. You can find the arc of approach, arc of recess. Plug it in over here, add them up, divide by the base pitch, you get your contact ratio. MC is usually number of, let's say sometimes it may come to 1.7 teeth per, like, like 1.7 teeth are in contact at any given. So Let's okay. So that's mostly about like things, parameters you need to know to design a gear. So let's go for some common problems that you can encounter while dealing with gears. Okay. So let's continue. Uh, Whenever two gears mesh, you have to take care of a very like frequent problem that occurs is called the interference. Okay, and this is a very problematic thing that leads to fail. Yeah, very huge friction and vibration and ultimately the failure of gears. Okay, so you have to prevent this interference. So what is interference, why does it happen, and how to prevent this? Okay, so we will try to learn all of this so in like as simple as possible. Okay, uh so I want to go back a little bit to a previous slide because that's the one you're familiar with. I've already discussed it, so let's go back here. Okay, so we have already reached the conclusion that the star whenever the addendum circle of one gear mates with the base circle of the other gear, that point is the starting of tooth engagement, right? And similarly, when the opposite happens, like the addendum circle of the opposite gear mates with the base circle of this gear, then that's when the disengagement happens. And this whole duration, this whole length is called the contact, right? And this distance usually have a limitation. Okay, and if you don't maintain this limitation, that's when the that's when interference happens. So what happens in between interference? Okay, so let me erase some part of it. This one, this one. Okay. So if you see, like in the other slide, we saw that the line of action was, like this one. I could have, similarly, I could have denoted the line of action like this. It's basically the same thing. Okay. So over here, let's do that. So it doesn't change as long as phi remains same, the as long as the angle between this and the line of action remains same, this phi remains same. Line of action can be like this or this. So both are okay according to how you're actually looking into the systems. For this figure, so if I draw the line of action, this basically the line of action is actually this one. Okay, this AB. This is the line of action. This is the line of action. Okay, and this line of action is is tangent to the base circles, right? And what happens is, for to prevent interference, prevent interference, your C point and your D point. C point is what? Start of tooth contact, and D point is what? End of tooth contact. For your uh, A is the point where the line of action meets the base circle. B is the point where the line of action meets the base circle of the mating gear. Okay, between A and B, your line of action at A point, your line of action is a tangent to the base circle. At B point and A point, they are tangents to the base circle. C is the start of contact. D is the end of contact. Okay, to prevent interference, the contact length must be between A and B. Your contact length must be between here. Okay, the contact must happen in this short region to prevent interference. Now, what is interference? So as you see, this is your teeth, and I told you your teeth has an involute portion and a non-involute portion. So the involute portion starts from the base circle. This section is the involute portion. This region is the involute portion of the other teeth. Now, whenever teeth mesh, that whenever gears mesh, gears mesh, their involute profile are the involute profiles are the one that contact. Okay, because involute profiles are the conjugate surface, and involute profiles ensures that omega 2 by omega 3 is equals to constant. They are the ones who are doing this. Whenever interference happens, involute portion contact is broken. Okay, what happens whenever interference happens? The involute portion of one gear contacts with the non-involute portion of the other gear. These are non-involute portion. Non-involute portion. Whenever interference happens, whenever this contact length is not maintained, this length of contact is not maintained, the involute contacts with non-involute. And this phenomenon is called interference. It creates huge amount of noise. So let's go back to our slide that we were just talking about. So it creates a very loud noise, wear and tear, friction, sometimes gears locks up. And if I show an example, it can behave like this. Okay, so over here, if
on
you
the
see,
base circle
look,
and
the
material
gears are
of
trying to
circle.
shaking. It's going to move,
What are
but
when the
so
top
look at this
area
one
of the
over here.
tooth
So
of
this
the
is the base
first gear
circle.
comes in
This is the
contact?
area under the circle, right? So this is the involute portion. This is the non. This involute portion of the this gear meshes with the non-involute portion of the this gear. Okay, and this is called interference. This creates like a huge problems, undesired effects in gears, and we want to prevent this. Okay, you don't want this. It like interferes with like this constant ratio involute action that you initially, the conjugate surface action that you initially desired, it directly interferes with it. It kind of locks up your gear, reduces the smooth movement, causes vibration, causes noise, causes friction, causes like velocity differences, velocity ratio, changes, and so many things. Okay, and that's why we want to ensure, to prevent this, what will happen? Your C and D point must be, let's say, it can be over here, it can be over here, okay? It can be over here. It must be between this, between A and B. It can be anywhere between A and B, okay? It can be at this stage, that the figure shows what? Figure shows this. In this particular figure, can you all see that in this particular figure, the one we are just talking about, point C, is it between A and B? No, right? It's beyond A, and this D point is beyond B. That means for these two gear system, interference is happening. And you can see, if you zoom into this part, you can see how this involute profile touches the one below it, the non-involute portion. So over here, what is happening? Interference is happening. Okay, this involute portion is contacting with the section below the base circle, which is a non-invisible portion, and interference is happening over here. That means very loud noise and wear and tear is happening in this case. Okay, and we don't want interference, so there are some ways to reduce interference. Many ways to reduce interference. One of the most easiest way is called undercutting. Undercutting, and that is like, if I show in this way, it's like, okay, fine, you are contacting over here, you are kind of locking up over here, then let me cut you like this. Okay, so what happens is, they say that if this is the one locking up, then let's cut this portion in here, let's remove this material, then they don't lock up, then then the non-involute portion won't come in contact with the involute portion. So undercutting is like basically removing material, solving a problem by just destructuring your gear and all that. Okay, and it's an easy solve, and the solution actually works, reduces the main problem that it causes, noises and wear and tear. However, look, this is your teeth. If you cut away this portion, your teeth now looks like this. Okay, and there is nothing over here. This reduces the strength of the overall gear teeth, and in the long run, they have, they can, like break apart because the base is less strong. There's less material in the base. Okay, so there are other solutions. You can add, you can change the pressure angle, you can change the pressure angle. So if you change the phi, the base circle kind of, like restructure themselves. So that can, like ensure that the non-involute profiles and the involute profile do not match. Okay. And another option is you can increase the number of teeth, more teeth. Okay, so basically you're changing the whole diametral pitch or number teeth. Then there can be another solution, like you basically, whenever you can use a larger pressure angle. So you can use a larger pressure angle. You can add more teeth. You can use shorter teeth. Teeth length. Okay, this is the teeth length. You can use shorter teeth. Shorter distances between addendum, dendum, and base cycles. And these are basically some of the solutions. These are advantages. Undercutting is the most easy. However, undercutting weakens the teeth. Okay. This is undercut. It weakens the below the ear, reduce overall strength. And there are many other solutions. So now let's actually start to like understand about gears. You have learned all the parameters that involves gears, all the circles. Now actually let's go for calculations. Okay. So the AGMA has standards. Okay. So when gears, whenever you're trying to uh, design gears, you must follow some standard gear sizes. Okay. And those are AGMA standards or NC standards. Okay. AGMA stands for American Gear Manufacturing Association. Okay. Association. And NSI stands for, you already know this, American National Standard Institutions. Okay. You already know ANSI standards. So gears have some, the AGMA has sets, the Gear Manufacturing Association has set some standards which we follow when selecting different sizes of gears. These standards describe relationship between addendum, dedendum, clearance, radius, fillet radius, tooth thickness, and everything. And gear association sets these standards because sometimes when you want to work with systems, you can change gears. You have a bigger gear, you want to replace it with a smaller gear, and you can do that if both of those gears follow the same standard gear. Okay? So we can interchange gears of different tooth number, different, like sizes, different diameters and everything and all that, as long as they are standard gears, and they have the same pressure angle and diametral pitch. Why they must be standard? Because only standard gears defined by these associations, they have, the formulas I showed you, 1 by P for addendum, then, 1 by 1.25B for addendum and all that. The standard gears follow the relationship. Non-standard gears are arbitrarily shaped gears, okay? And they don't follow this relationship. So even if you have the same pressure angle and diametral pitch for those gears, the addendum-dedendum relationships are not maintained. So you cannot simply interchange between them. So again, I'm repeating, the OGMA and the ANSI standard states that if you want to replace one gear and mesh it with another gear or replace that particular gear, even if they have different diameter, like pitch circle diameter or different tooth number, it's possible. Interchanging of gears of different properties is possible as long as they have the same phi and same diametral pitch, and they are all standard gears. Okay, standard gears. Okay, the sizes of teeth used are chosen by selecting the diametral pitch P or the module M and all that. So there are two lists given over here. So this is again from your Shigley chapter 5 book. So this one is table 7.1. These actually gives you tooth sizes, the tooth sizes, or you can call it diametral pitches. In US customary unit, FPS unit, basically what is the tooth size per inch, and this is the standard. And only these sizes, only these diametral pitches, only these values of diametral pitch, only these values of module are the standards. Okay, standards, and they follow the relationship. Any other diametral pitch, any other like gears having any other modules, they are not standard, they are non-standard gears. Okay, and you cannot interchange them. Okay, so basically, let's say in here, this is actually the how it was produced, how the manufacturing system, how the tooth were manufactured. So if your two teeth have the same pressure angle, 20 degree, they follow this relationship. And if their diametral pitches are 1.25, you can interchange them. If the diametral pitches are 4, same diametral pitch, you can interchange them. So pressure angle and diametral pitch are same standards, and you can change them in interchange. So that's all for the basics of gears. I will end my